the topic for this session, I think it's been announced already, but tracing service dependencies at scale with Druid and Flink. A little bit about us. I am Sudeep Kumar. He already has introduced me pretty well, so thank you for that. Beyond that, I am part of the Monitoring Cloud organization, and the co-presenter with me, Nilesh Kurade, who is a senior product manager, is also part of the same larger team. Now, our organization provides a comprehensive one-stop solution for all the Salesforce observability needs. That means we have managed tags for metrics, events, logs, and traces, also commonly referred to as the MELT stack. We are responsible for delivering observability for thousands of different applications across different application stacks, regions, environments, infrastructure. And in a large enterprise company like ours, you can imagine the immense scale at which we operate, right? We kind of process millions of telemetry signals every second. Today, during the talk, we'll delve a little deep into one particular use case of inferencing service relationships or service dependencies, by which, or in this particular scenario, or in this use case, we process millions of events every minute on our streaming pipeline, and then subsequently make them available on our events backend, which is powered by Druid. And later part of the talk, in the later part of the talk, Nilesh will introduce us to our event store, which is providing Druid backend for us, how we onboard users, how we maintain, manage, and scale our Druid infrastructure. Now, let's come to our problem statement, right? What are we trying to do with this use case? It primarily has to do with the curse of microservices, right? Now, every organization will be able to relate to this. There are just thousands of microservices and new ones cropping up for no good reason sometimes, right? While this, if you look at the microservice architecture itself, over last several decades, it has served us well in terms of how we scale out features by keeping good separation of concerns and all other different goodies that come with microservice architecture. However, it has its own set of drawbacks and which often gets overlooked. And these are relating to tracking dependencies, especially if you imagine a large organization like Salesforce. We have multiple teams handling different microservices. We don't know how these dependencies are taken between services. And many times, even though you are aware of the dependencies as you create the service, over a period of time, the service interactions change. They are never static. They keep evolving. And defining SLAs, SLOs for your service can be especially challenging when you don't know what kind of service you are taking dependency on and what is their availability. There is no easy way to drill down into inter-service request flows. Now, we are all aware of metrics. Metrics does give you a good view within your application scope. However, it doesn't really speak about issues on inter-service boundaries. And identifying macro-level transaction patterns, right, with respect to your errors, latencies, duration, for external service calls can also be quite hard. Given all this backdrop of microservices, how did we infer service dependencies, right? It was awkward to say the least. So the way we did that is we would ask our developers to come to a particular repo where they would declare themselves as a service owner and also would mention that what kind of dependencies or what kind of services they take dependencies on. You can quickly see the problem with this approach, right? Like, it's never up to date. You really can't use it as a source of truth. And often, whenever an incident happens for a particular service, people depend on tribal knowledge to actually infer what kind of dependencies you have. They do all kind of unique stuff as well. Sometimes they look at the firewall rules. They see that, okay, this service has opened up access to other service, so possibly they are talking to each other and things like that. But clearly, that's not the way to go about it, right? And this is exactly where distributed tracing as a concept really excels and shines. So for folks who are not familiar with distributed tracing, you can actually track an individual request flow as it goes across different applications. Now, as a request goes across different applications, it's trying to attain a particular common workflow or a goal. Now, each of these request flows are represented by span events. We will get into the semantics of what a span event is later on. But the request itself is a collection of span events which are tied to a particular GUID identifier. With distributed tracing, what you could essentially do is to look at all the different unique request flows that happen in your system, kind of aggregate them, and try to infer dependencies across your services, saying that, okay, this is a relationship between this service and, say, another one. So what does it help, the distributed tracing in general? It would answer basic questions like, how are my services used? Who depends on me? And it would also help you to track the dependencies of your downstream services. You could also, once you have like a nice visual pattern, be able to discover unsafe, unwanted access patterns. Like, why is this service talking to this service in this environment, and so forth. And it is also quite useful to understand bottlenecks, especially on the service boundaries. And hopefully with all of this, you would be able to reduce the time to remediate issues, especially on the inter-service calls. One important disclaimer, to do this effectively, you need to be able to support tracing everywhere, right? And our team in particular has worked quite hard over 18 to 24 months now to be able to support tracing across different stacks, different regions, different environments, etc. Now let's look at what distributed tracing semantics is, what a particular event for us means, and how we kind of would represent them, right? So consider a request flow, which is depicted on the left side of this particular slide, where it goes across different applications, say S1, S2, S3, S4, and S5. And each of these services would emit set of records or set of events, which we refer to as spans. For example, in this case, S1 is emitting spans A, D, and H. Now, each of the span event has some metadata with it, which kind of mentions what kind of operation was performed within the particular service, when did that particular event happen in terms of its timestamp, what was the duration of that particular event, and a lot of other metadata associated with it. So similarly, all your individual other services would also emit their own independent spans. Now, all these span records are tied to a particular GUID or something called as a trace ID, and that's how you essentially track a request flow. Now, if you have to convert that particular model that I just described on the left, you can depict it as a nice waterfall model as shown on the right, wherein you kind of overlay the root event or root span, under which you'll start placing your child spans. Now, each span has a parent span associated with it. That's how you kind of establish this hierarchical relationship. And the placement of the span in the waterfall depends on when exactly that span event happened, and the width of the span would be based on the duration, right? And this is a nice waterfall that you generally get when you are trying to look for a request, a trace. Now, you have these n number of request flows arriving on your system. You are able to infer them. Can we do something more with it? This is essentially what service dependency is trying to do. So what we do is we look at all the different requests that happen on our system, request flows that happen on the system, aggregate them uniquely to be able to produce edges. Now, with edges, you can represent relationship between services. For example, you do all different aggregations, aggregations on all different requests that are arriving on a system and kind of create this dependency diagram as shown on the right, wherein, say, S1 depends on S2, S1 depends also on S3, S4, and S3 depends on S4. So you have now a basic dependency graph, which is a great win already for us, because with which we are able to show how services talk to each other within the scale of Salesforce, right? Now, while that is useful to say, okay, how are services talking to each other, it is also useful to be more granular in terms of saying that, okay, which operation within a service is actually depending on the operation on your next service, right? So you need to be more granular in that way. So our schema on Druid kind of represents this as well. We'll talk about it more in the later slides, how this entire schema is represented on Druid. And now let's talk about, okay, you have this use case. We explained what the problem statement is and how distributed tracing can help. Let's look at generating this dependency graphs using Flink and Druid now. Now, before we even embarked on creating a system around Flink and Druid, there were a few key considerations to make, and it is important for everyone to actually go through some of these questions in their mind as well. First, is there a need to build trace sessions to infer dependencies? Now, that means you have to be able to logically collect all spans associated with the trace somewhere. You could do it once you persist it on your backend, say in Druid, for example, or you can do it upstream in some kind of streaming pipeline. Now, both has its own advantages and disadvantages. I would actually lean towards saying that it's more harder to do it on your storage than moving this problem a little more upstream. So we kind of moved in that direction, wherein we are creating these trace sessions and processing all these records on a streaming pipeline, and then subsequently kind of persisting onto Druid. And did we need to do processing all 100% of traces to infer service dependencies, right? Now, this is a large amount of data that we are talking about. So this was an important consideration that we made, that we said, okay, let's look at only a subset of traces, and possibly on a macro level, it should be sufficient for us to infer relationships. And based on what we found, that was actually true. So we don't look at all the 100% traces, rather we only look at a subset of set. And these are the choice everybody should actually kind of also look at while actually building a system like this on streaming with some kind of backend like Druid. And another question on my mind is, do you need to collect all spans within a trace context? Now, as I said, a trace is a collection of span records, but only few span records really gives you relationship between service boundaries. And so we kind of only looked at those. So rest of the thing we kind of eliminated it and thereby reducing our load on our streaming pipeline. Another question, can it be and all this kind of feeds into, can we do it in a cost-effective manner? And we wanted to use existing managed stacks like Flink and Druid. Now, we are a user of Flink and Druid. We have dedicated teams who actually manage Flink and Druid for us. So we didn't want to spend time maintaining that infrastructure really. So this was a conscious decision to see, okay, what we can use to actually build this particular use case. Another consideration is what kind of sampling would work. Now, this is a little bit involved topic when it comes to distributed tracing, so I'll not go very deep in this particular point. But it is important to be representative of all the different transactions that happen in your system. Because if you are sampling data, you basically are saying that you're filtering out things. So you should be careful about what you filter out to be able to give more representative service dependency graphs. And another consideration, okay, now you have everything, say, persistent on Druid, they have a time associated with it as well. You can basically create metrics out of trace data, which is called as red metrics, which stands for request, error, and duration. Now, since we are running on sample data, it is always a question that whether these red metrics are useful or not. What we found is that the shape of the graph that these red metrics represent is often enough to indicate larger macro level issues that might happen in your services. You can use it for any kind of anomaly detection as well. So that was good. And did we need fully transaction service map? Now, somebody who wants to create a dependency graph would directly pivot towards some kind of graph database, right? To say that, okay, you need relationships, you need some kind of hierarchy. But do we really need that? And does it really work at scale? So we decided not to go in that direction and keep it very, very localized to a particular service scope in terms of its dependencies upstream and downstream. And we'll talk about that later on. And can we enable alerting on inter-service interaction health? Since we are using Druid for all of the storage of all the events, we wanted a system which can support alerting. And our event system, which is based on Druid, did support it. So thereby which we can say, okay, a new service dependency kind of popped up for a service and et cetera. We can actually get visibility into that. Now, why Flink, right? One, I said it's an obvious choice because it was existing as a managed offering for us. So it kind of made things easier for us not to actually run Flink on our own, but only to create our own jobs and deploy on Flink. And Flink has this good, nice ability or a concept of windows through which you can create large number of concurrent trace sessions. We are talking about millions of concurrent trace windows that we kind of, session windows that we kind of keep it open. So it has a nice ability to do that natively. And on Flink, you can also then sample, filter, enrich, do all kinds of different processing, which is also great. And then it has nice aggregation capabilities, which you should be looking at to kind of reduce the load on your backend, say in this example, Druid. So we aggregate data as much as we can before actually storing anything on Druid, which kind of helps us to scale, because imagine the kind of volume that we are talking about here, right? And there is, of course, availability of standard things like Kafka for downstream consumption, and Kafka is a great right-hand lock that we can always use in case of any availability issues. So it also fit very nicely for us. And why Druid, right? Again, a managed offer within organization, an important point. And Nilesh, as part of his talk, would actually expand upon that, on what this events platform is and how we kind of maintain the platform. But apart from that, it was already known to us that it scales very well for multiple events use cases. We have a lot of critical use cases already running with Druid today. And we have some support to actually do alerting on events data. There are some restrictions around it, but we kind of are comfortable modeling our data around modeling our data in such a way that we can enable alerts on it. It is well established within the organization that Druid has given us blazingly fast query performance, and we wanted to actually use it for our particular use case. And you can have additional storage-based aggregation rules, as in you can keep rolling up the data based on your time interval, reduce the overall storage requirements on your Druid, and so forth. And it also provided us a long-term retention when compared to our traditional trace backstore, where we store data only for 7 days, but in Druid we can go up till 30 days, which is also nice. Later, as in the presentation, Nilesh would actually cover in greater detail why we chose to go with Druid for more general perspective, right? And today, if you have attended today's morning talk by Eric, he mentioned whenever you think about more use case with Druid, think about events and think about entities. So in this case, this is the entity equivalent for us, wherein we are saying service dependency graph is nothing but a combination of nodes and edges, which should be quite obvious. And the edges connect nodes, and often the direction of the edge represents the relationship, right? And this is how we actually wanted to structure our data on Druid. And you can have your own definitions of a node, really, saying that, okay, you have service, subservice, operation, and scope. That's what we use, but you could essentially use anything for it. Basically, this is our high-level, this is our Flink pipeline with Druid backend. So you can imagine we receive a trace stream with millions of traces coming every minute. And then we have a filter processor, which is rule-based. We kind of filter out things, sample the data based on trace IDs, and then split the traffic based on the trace ID hash. As we split the data based on trace ID hash, we start creating trace sessions, where we collect all the span records for a particular trace in a particular window. And as the window closes, we have a pre-configured time for which a window is kept open. As the window closes, we emit edges. Now, these edges are in very raw format, and in the subsequent processor, which is an edge aggregator, we kind of roll up all these edges for a particular interval, like 5 minutes, 10 minutes or so, and then kind of write everything onto our data bus, which is Kafka, through which it's made available onto Druid Store. Once it is available on Druid Store, there are multiple ways users can consume this data. They can do it. They can plot time series on Grafana. They can slice and dice the data using the superset. And also, we have provided our own set of standard APIs on a platform called Tracer, through which you can surface this information in a very hierarchical fashion on a custom UI. Now let's come to the modeling of the data, right? Now, as I said, a trace is a request that goes across different services. So there is a place where essentially a request starts, right? And if you consider this particular workflow, the trace actually started from service A, going to service B, then kind of forks into service C and service D. But service A is the one who originally started the request. So what we kind of decided is that whatever we model, we will anchor our records to the root service. right? And that's essentially what we did in the bottom table. If you look like, you have source, you have destination, which kind of represents the edges, but we anchor everything onto the root service, service A or operation 1 and so forth. So an advantage of doing this way is that you really don't need now like a graph DB, wherein you can say that for a create account, for a use case, plot me the entire transaction dependency map, right? In one shot, you can get everything associated with that particular root service and the root operation, which is great. So that's one way you could like plot entire transactional dependency maps, service maps, and then you could also now represent adjacent dependency edges by the way we demonstrated here, wherein if you look at here, the service B is dependent on service A, while C and D takes a dependency on B. And by the concept of the source and destination columns, we kind of fill that appropriately. Like B would be service destination for service A and will be the source when the destination is service D, C and D. So immediately you can say how your services are interacting upstream and downstream. And there are metrics associated with each of these columns relating to count, error, and maximum duration. Another interesting thing we kind of ended up doing is that as you're aggregating things on your Flink, right, and you want to write everything onto Druid backend, can we write some non-aggregated attributes insert non-aggregated attributes into the rolled up edge record, right? That's exactly what we try to do here. Like for every aggregated record, we kind of introduce some trace samples and we inject them into few columns so that you know for this particular aggregated record, which particular trace sample gives a representation of it. So by which users can quickly jump to that particular trace view for this particular aggregated record, which is again a great feature that we could actually enable with this kind of modeling. You can always have these aggregations done and do this dependency graph, but also since time is a part of the record, you can plot time series out of your contributors. Like for a particular, say, transaction, what are the different contributors that happen from different services? For example, in this use case, you can see authentication is taking the most time, right? Something to optimize on. And that's kind of another insight that we could drive from this kind of service dependency map with Druid. Sorry for the form factor, it might look a little hazy, but the idea is that users would come to the portal, they select their one particular API, they select their different attributes against environment, and then we have few other attributes as well, and they select a time range, right? And for the time range, we kind of plot the entire dependency, saying that this service is dependent on this service. The green would show kind of healthy relationship, the red could show some kind of error relationship between the services. Now, one thing that is interesting here is to remember that we are doing live dependency transaction service maps here. So it's time range is a big part of it, right? So once you have something like a time range for which you can plot the dependency graph, you can compare, say, week over week and things like that, which is and then create alerts out of it, which is quite a compelling use case for us to actually enable for our users here. So you can, and once you select a particular edge, you can expand it later a little more, and then you would see set of trace IDs associated with it. That's the schema that we talked about later in the previous slide, wherein you are spraying some trace IDs for every aggregated edge records, and you can go to that particular trace view directly from this service dependency map. So that's way users can quickly drill down to their problems by looking at workflows which kind of are indicating there is something wrong between relationship between two services, right? Okay, now we rolled out this feature, service dependency. We were quite enthusiastic about it, but quickly we started getting the feedback that our service graphs were incomplete, and many times relationships didn't show up. So that kind of led to us to think about the problem a little more deeply, and we created another pipeline with Flink and Druid to be able to look at broken traces, wherein you have spans that actually got missed out in your trace, and due to which you don't have a complete picture of the service dependencies. with which we found out different patterns that actually occurred in our infrastructure. Like we had issues with mesh infra and many other such similar use cases, and we worked with them closely to actually improve our data quality. And it's been very useful for us to give more complete dependency graphs. So with this, I will conclude my part of the talk, and I will invite Nilesh over to the stage. Thank you, everyone.
In this part of the session, I'm going to walk you all through our almost 3-year-long journey of operationalizing Druid at Salesforce and making it work for our scale. Know that this journey is still ongoing, and so a lot of what I'm going to talk about is already in place and functional, but I'll also end up touching upon a few things that are in flight and that are on our roadmap. Before getting any further, I would like to share with you all a little backstory about what really drove us, the problems that we were running into that made us look outside, and which led to us adopting Druid in our observability platform. So this is the vision for our cloud. We strive to provide an observability platform that is tailor-made for Salesforce to empower customer success by enabling highly available products. Until about 3 years back, we were far away from this, and there were a few challenges that we were running into. With the growth of the company and migration towards cloud native infrastructure, primarily, the cardinality of both our business dimensions and infrastructure dimensions were growing manifold. And the foremost challenge that we had was inability to support this high cardinality telemetry data. And that made it really hard for us to deal with some of the important use cases during incident management, such as, for example, we were not able to comprehend the blast radius of incidents. It was very hard or time consuming to answer some of these questions that is really time sensitive when an incident is ongoing. For example, how many of my customer organizations are affected by this incident? Is this related to a specific set of virtual hosts to which the release was made in the latest staggered release? It was hard for us to discover issues before our customers did. We were trying to be proactive and notify customers for situations such as when any user from any of our customer orgs would reach their predefined limit for a specific service. All of this and what Sudeep just spoke about, right? So service dependency. So all such use cases, they really needed support for high cardinality telemetry, which we lacked. The other important thing that was missing in our observability landscape was building sufficient or enough insight into our infrastructure. And so that made it hard to explain changes in metric trend lines. For example, when we saw a surge in our latency chart, was it related to something happened in the environment? Was it due to a recent release that happened, or was it due to some recent campaign which led to a surge in the user requests coming in? And all of this then led to basically the net effect was that our TTD, time to detect, was higher, our response time was higher, the time to restore was very high. We were spending a lot of time going through massive amounts of logs. So we were able to overcome these challenges. Of course, you might have guessed through building, having a platform that is based on Druid to support high cardinality telemetry. And to understand this better, let's look at how the cloud looks like as of today. This is an overly simplified view of the platform, just to clarify. However, it captures all the necessary parts for the purpose of this talk. As you can see, we have support for, today we support all these 4 telemetry types from the MELT quad: metrics, events, logs, and traces. Metrics is backed by OpenTSDB and HBase and Splunk. We use Splunk for logs. We use Elasticsearch for traces. Events is covered by Druid and all of that. But it did not look like this 3 years back. There was a gaping hole in the system by not having support for events. And why are events so critical? So I know a lot of you might already be aware, it has been talked about quite a few times since morning, but for the benefit of the others, really quickly, events are occurrences of this, any notable changes that happen in your system. They could come from your system, infrastructure, observability, they could be related to your workloads or applications. They could come from business, such as, for example, user click streams, a new customer onboarding, a promotional event happening, and so on. Structurally, they are composed of key value pairs. A bunch of them are for measurements, so metric data, and the remaining ones basically provide dimensions. And you can have a large number of dimensions compared to traditional metrics. A lot of dimensions basically they identify the event, the service or the application to which the event signal belongs to. There are dimensions that allow you to correlate with other telemetry signals. There is other forms of metadata that make it really useful for using events for many other purposes. You can provide logs and exception traces in events. And that gives some key characteristics to events as a telemetry signal, making them really high fidelity. They are rich in content. There is no loss of information. It's at the highest level of granularity. And it allows you to carry high cardinality dimensions such as customer org IDs, request ID, URI, user ID. The ingestion lag is low. The query latency is high. And sorry, what is not visible here on the screen? So there is this fine print with asterisk. So all of this, while the nature of events allow you to support, it needs to be powered by appropriate technology. And that is where Druid really shines. And it really enables events as a use case. And that is where we were able to get these key benefits, which in the end allowed us to address the challenges that I spoke of. So we are able to now, we have a lot more flexibility in terms of how we roll up data, how we slice and dice around high cardinality dimensions. Our aggregates such as percentiles and histograms are a lot more accurate, meaning that our decision making is a lot more accurate. Our alerts are accurate. If we are using auto remediation, those decisions are accurate, and we more often than not we get what we want. Events basically provide context for other telemetry signals. Suddenly that bumps up the value of those signals. So essentially you understand why there is a certain change in your metric trend line. So it becomes a lot more useful now. So before getting into the actual platform, how our event platform looks like, a quick overview. It's powered by Apache Druid. We support streaming ingestion that is based off of our open telemetry based instrumentation libraries and agents. We also support batch ingestion through S3. So the same platform caters to real-time queries as well as analytics queries for faster response times. We support charting, dashboarding, querying through Grafana as well as our in-house monitoring portal. SQL is the query interface, as it is offered by Druid. We support alerting on these events through our own proprietary alerting engine. Out of the box, we support 30 days of retention for all these events. The cluster is deployed, all our clusters are deployed in Amazon EKS through Salesforce's public cloud fabric layer. And we use Druid Kubernetes operator for managing our clusters. This is how it roughly looks like, each of our Druid clusters. So we have all these data nodes that are deployed using Kubernetes operator for Druid as stateful sets. We use S3 for deep storage. We use RDS for metadata. All our transport is offloaded to managed service mesh that is based on Istio. So all the intranode communication is MTLS and all managed by the service mesh. All external communication with outside clients is also through Istio Ingress Gateway. Again, it's a managed service for us. At this time we are using EBS volumes, GP2 volumes for historicals and middle manager storage, but we are evaluating EC2 instance stores for faster performance. Anything else? Yeah, and our data pipeline, the streaming data pipeline comprises of Apache Flink and Kafka. Flink allows us to combine multiple streams of events that are destined for the same data source into one stream that is fed into a Kafka sync topic, which is where the given data source consumes events from. Today, I think one of the reasons why we went with Flink back then, about 3 years back, was because at that time Druid did not support being able to ingest data into the same data source from multiple Kafka topics. That support exists today, by the way, but outside of that, we also had other reasons, such as being able to have configurable routing, so teeing off some events to some other store based on some rules, or having streaming alerts. So that's why we like to have Apache Flink in our pipeline. What made us choose events for our Druid for our events platform? So we really like its column orientedness. It works really well for our query patterns, and the fact that it partitions by time, it works because all our queries have a time, time filters. It provides faster query response, streaming and batch ingestion options, the deep storage through S3. One of the key features that Druid offers is fault tolerance and automatic recovery in the event when one of the data node goes down, or even in the event when the entire cluster is wiped out. Druid has the ability to restore everything from the deep store, which really works very well. The Lambda architecture helps us fulfill both analytics, real-time queries and analytics queries that require us to look, query the real-time segments as well as the older historical segments in one query. The SQL interface is very powerful. We also use nested columns, rollups, and query laning, and many other features. So while you look to use Druid for building such a platform, it is important to note that the platform Druid is highly configurable, and while most of it works out of the box for common use cases, for special use cases you need to fine tune it and to get the desired performance and outcome. In our case, we use hourly granularity for segments. We have compaction enabled for each of our data sources. We try to maintain segment sizes between 300 and 700 MBs for optimal performance. We have a lot of group by queries because of how we have implemented our alerting, again to optimize our alerting management. And due to that, we have merge buffers configured for brokers. We have about 20 merge buffers, I think each with 500 MB size, and we have 5 brokers in one of our largest clusters. Our historicals have 4 terabytes of volume at this time, and we are evaluating instance stores for improving performance. HA, I think I'll get deeper into it, but HA is achieved through segment replicas and tiering for historicals. And then we use Prometheus emitter as an extension for getting higher visibility. So this is how we are achieving HA for Druid at this time. We have each segment we have a replication factor of 2 for each of our segments, and our historicals are deployed in 2 tiers using 2 stateful sets. Each tier gets one of the stateful set, and data sources are configured to assign 1 replica to each tier. And then we use Kubernetes pod node affinity to ensure that each stateful set is bound to a different availability zone. And we use a pod disruption budget that is common across these Salesforce stateful sets. All of this helps us achieve AZ fault tolerance. So even if one AZ goes completely down, we always are, for example, in the event of host patching being done by Kubernetes cluster operators, or we running rolling updates to our cluster, we always have at least 1 segment for each of our, 1 replica for each of our segment available for responding to queries. And the last bit that I want to cover is how we are onboarding events, events use cases. So for we categorize our events use cases broadly into 2 categories. Those that are very common, they are termed as standard use cases. Their schema is predefined, it is pre-onboarded. The instrumentation in many cases is automatic, out of the box. Users don't do anything. They get all these events such as AWS infrastructure events or transaction events for APM, all of these out of the box. The other categories of events are what are use case specific. They are user defined. That is where we require users to specify how the schema looks like, and we onboard that schema and then set up data pipeline to ensure we are able to ingest data for these custom events. This is how the onboarding flow roughly looks like. So users submit a pull request with the schema, which is based on Druid data source ingestion spec. We have slightly enhanced that to make the ingestion spec self-describing for users. So users are able to provide some metadata that describes the overall event type, what it is for, and each of the fields within, and the versioning of the schema. Once the pull request is merged, our onboarding automation picks it up. The ingestion spec is it provisions data source on Druid side, and on the data pipeline side, we set up Kafka topic for the ingestion to happen, and we also set up rules in Apache Flink for setting up the ingestion pipeline. Yeah, these are some numbers. We are still at a very early stage. We are just about beginning. But as of today, our largest cluster is ingesting about 10 billion events a day. Overall ingestion volume stands at 20 terabytes of events being ingested every day. We are serving 600,000 plus queries a day. Our highest high cardinality dimension has 70 billion plus values. Our ingestion lag is actually, we officially state it to be less than 30 seconds, but more often than not, we get ingestion within single-digit seconds. Our P95 query latency stand at sub-second level. We have about 150 custom user-defined event types onboarded, and we are serving more than 600 alerts. These are all alerts, but the actual time series that we evaluate is a lot more than this. Yeah, that's about it. This is our roadmap. We are looking to use tiering to solidify our high availability. We are looking to use query laning for service protection. Looking forward to window functions going GA. We are looking to support higher retention through Salesforce's data lake. And as I said, instance store for historicals for faster response times and ingestion time rollups. Some of the items that are on our roadmap. That's about it. Thank you.